diagram we're going to do is figure 6.3. We've got two parallel branches, two resistors in the first branch, and one resistor in the second branch, right? And R1 is 8 ohms and R2 is 4 ohms. R2 equals 4 ohms. And R3 equals 6 ohms. Our total voltage for this circuit is 12 volts. Voltage total equals 12 volts. And then they ask us to solve it. Again, the first step on all of these is always to find my total resistance. And to do that, I have to simplify the series and the parallel until I get down to one resistor. So as I look at this, I look at what I have. Do I have any simple series or simple parallel? Well, I have no simple parallel because R3 is in parallel with the combination here. I have to simplify that series. And why is this series? This is series because R1 is in one path with R2. They're directly connected in one path. So that is series, and so I'll connect them with this series circuit. So I'm going to simplify this by drawing the next simplified circuit diagram. Like this. Our V total still equal 12 volts. This will be R1, 2, and of course R3, we already know is 6 ohms. So we got to solve and simplify those two in series. And we know in series that R1, 2 is going to equal R1 plus R2 because in series resistance adds. And so if I add these up, this is 8 ohms plus 4 ohms, so that equals 12 ohms. So I put that into my new circuit, R12 equals 12 ohms. And now I have my new circuit. We'll call this circuit A, right? We've simplified it down. Now we just have two pure parallel circuits. How do I know they're parallel? The top part of both resistors are touching at the top. The bottom part of both resistors are touching at the bottom. So they are connected top and bottom in parallel. We're going to have to use our parallel equations for this, and we'll have to set up our next simplified circuit, which is going to give us our total resistance. We'll simplify it down to one resistor. This will be R1, 2, 3. Now they're not equal here, so I can't use the equal shortcut, but I do have two of them, and there's a shortcut for total resistance for two resistors. Again, I can always use the reciprocal equation, but I don't like the reciprocal equation, so I'd rather use the shortcuts when I can, and in this case I can. So R1, 2, 3 equals R1, 2 times R3 over R1, 2 plus R3. This is called product over the sum, and it's a shortcut for two resistors. So in this case, R12 was 12 ohms times R3 was 6 ohms divided by R12, 12 ohms plus 6 ohms. Okay, so 12 times 6 is, what's that, 72? And 12 plus 6 is 18. So take the calculator. Make sure I did that multiplication right. 12 times 6 is 72 divided by 18, and that equals 4. So R123 equals 4 ohms. The total was 12 volts. Okay. So once I have that, I know my R123, which is basically R total, is equal to 4 ohms. So R total equals 4 ohms. We solve I total the same way, using Ohm's law, which is V total over R total, and that's 12 volts divided by 4 ohms. And so my I total equals 3 amps. So we have all our totals now at this end. From here, I have to solve across over for the current in each of these branches and then solve for the voltage drops. Now in parallel, there's some things I can do that will help me with this. And one of those things I can do is that I know in a loop the voltage will equal. And since if I do the back end loop, there's only one resistor, that's the easiest one to solve. There's only one resistor, 12 volts in a loop. That means I know VR3 equals 12 volts. In other words, there's only one resistor in that loop. I got 12 volts on the battery. I have to have 12 volts on that branch, which means R3 drops 12 volts. Now you want to do the simplest things first because that helps you to solve the problem easier. I can solve for current in R3, the back branch. That's just going to be V divided by R. VR3 divided by R3 is 12 volts divided by 6 ohms, and that equals 2 amps. So I know I got 2 amps. This is our node. I know I got 2 amps going that way, right? I know my total current coming through here is 3 amps, which means I got 3 amps coming into that node. Okay, so these series parallel circuits are like a puzzle, and you want to solve the simplest part first and then see what you have left. Since I have 3 amps coming into the node and 2 amps leaving on the top, I have to solve for the current going through R1 and R2. Basically, you got to remember Kirchhoff's current law, which says all the current entering a node equals all the current leaving a node. In this case, the total current here is going to equal the current through R12 plus the current going through R3. So this would be 3 amps minus 2 amps leaves me with 1 amp going through R1 and R2. So now I know IR1 equals 1 amp and IR2 equals 1 amp. And how do I know that 1 amp goes through both? They're in series. Current flows in series. It's the same in series. All the current here flows through both of these resistors. When we get to the bottom node here, the same thing is happening that we did before. I got 2 amps coming back through this resistor to this node, and 1 amp coming back through this first branch to this node, and then I have 3 amps going back to the battery. So 3 amps leave the battery, 3 amps come back to the battery, and I have a complete system. So we've used Kirchhoff's voltage law and Kirchhoff's current law to solve this series parallel problem. The only thing I have left is the voltage drops on R1 and R2. And again, VR1 just equals IR1 times R1, Ohm's law, which is, of course, 1 amp times 8 ohms. And so VR1 equals 8 volts. And we do the same thing here. VR2 equals IR2 times R2. And that's going to be 1 amp times 4 ohms. And that's just going to equal 4 volts. And so I've solved for everything. I've solved for the current in every part. I solved for the voltage in every part, and I know the whole system. So we have solved this. Again, this was resistance strings in parallel.